Hello and welcome to this Royal Society videocast. Today we'll be hearing from Dr. Moira Wilson, Senior Lecturer in the School of Mechanical, Aerospace and Civil Engineering at the University of Manchester. Moira and her colleagues have an article in Proceedings of the Royal Society A from May 2009 called Dating Fired Clay Ceramics Using Long-Term Power Law Rehydroxylation Kinetics, which is a bit of a mouthful, Moira. What it means that you've found a way to date ancient ceramics. In fact, you've found the only way that currently exists.
Yes, the widespread perception seems to be that carbon-14 dating can be applied to anything, including ceramics. In fact, carbon-14 dating can only be carried out on things that have been alive and exchanging carbon with the atmosphere. So this technique dates the ceramic material directly, doesn't require any external calibration data. In fact, it's self-calibrating.
And what you're holding there is a Roman brick.
Yep, well, it's a Roman tile, actually. And from the minute this came out of the kiln 2,000 years ago, it started to chemically react with atmospheric moisture. So for 2,000 years, it's been reacting with moisture, it's been getting heavier, it's been expanding and getting bigger. And I think most people think that a brick or a ceramic is completely inert, actually. In fact, it's very reactive.
And you've worked out the law which governs this chemical combination with water vapour.
Yes, we found this new rate law. That, so it means that the mass gain and the expansion is occurring at a precisely defined rate, and it happens to be proportional to the fourth root of time.
It's really like revealing an internal clock in the ceramics.
Oh yes, essentially this is a clock, yes. It's combining with water molecules at a precisely defined rate, so yeah, it's a clock.
And when it does combine with the water molecules, what happens to the glaze? We've got another sample here, haven't we, that we can see what actually happens.
Well, the basis of the method is moisture expansion in fired clay ceramics, and everybody is actually familiar with this, even if they don't realise it possibly. And this is the most common manifestation of moisture expansion, is this crazing in the glaze of ceramics. And this is caused by the substrate material. So what's underneath this glaze is this, essentially, that's expanding. The glaze, this glassy material, is too brittle to accommodate that expansion, so it cracks. So everybody's seen this. So everybody's actually quite familiar with it. What they're probably less familiar with is that alongside the expansion, there's this mass gain going on as well. So the mass gain is the more fundamental process. The mass gain is the chemical reaction. The expansion is the consequence of this.
And how big are these effects? I mean, say we take the terracotta warriors, for example.
Ah, right. Well, we worked out that a terracotta warrior over its lifetime has gained about 4 kilograms, which is quite a lot. It's a big effect. You know, it's not some barely measurable effect that we can hardly detect.
And if we had a wall made out of terracotta bricks, that must be expanding.
Yes, a kilometre of wall will expand by about 1 metre in 200 years.
It's a big effect.
It's a huge effect. It's a very, very easily measurable effect, yes.
So Moira, tell me what you do. I mean, say you want to date that brick. We do in fact know how old it is, but if we didn't and you wanted to find out its age, what would you do?
Well, this, as it sits now, the mass of this is the mass as it came out of the kiln 2,000 years ago, plus the mass of water with which it's chemically combined over 2,000 years. Okay? If we reheat this at 500 degrees, that's a sufficiently high temperature to drive off this chemically combined water. So if we weigh it again after we've reheated it, we can measure how much water it's lost, how much chemically combined water it's lost. Having done that, we start to weigh it, and it will gain mass again, according to our time to the quarter law. So it will be linear with time to the quarter. So we measure the mass gain for sufficient time to establish the rate at which the mass gain is occurring. And then it's a simple matter, if you know the rate at which the mass gain is occurring, to work out how long it would take to recombine with the water that we've just driven off during heating. So it's actually very simple.
So what sort of effect are we talking about? I mean, if you've got a brick that weighs, say, 2.5 kilograms, how much weight will it lose?
About 10 grams.
So again, it's a noticeable effect.
Well, it is a big effect, and 10 grams, depending on how many decimal places you're measuring to, can be a lot of measurement units. So if you're measuring to 1,000th of a gram, that gives you 10,000 measurement units. So it is a lot.
But you're working in tenths of millionths of grams, aren't you?
Yes, yes. So the experimental methodology sounds incredibly simple, but it is incredibly simple, but to actually do it, the microbalance is extremely challenging. You know, it really is hard to get an experimental result.
Now, the temperature is crucial in all this, isn't it? Tell me about the importance of the temperature.
Right, well, the first dating trial that we did, we carried out all the measurements at room temperature, and all the results came out wrong, all by the same amount, which was a bit alarming, but it was quite reassuring that they all came out wrong by the same amount. And then we acquired this microbalance, and we started doing experiments at different temperatures, and that's when it dawned on us that because we have a chemical reaction going on, a 10-degree rise in temperature will double the reaction rate. It's all very obvious in retrospect, but it wasn't at the time. So what we were doing in our first dating trial was actually trying to date something at 2.5 times the temperature at which it had spent its life.
So the temperature at which it has spent its life
Yes.
is crucial?
Yes, it is.
Because that determines the rate
Yes.
of the chemical reaction?
Absolutely.
Yes, and so when you do this reheating and the calibration and so on, you have to do that at the same temperature
Yes.
as the specimen was
Yes.
for its life.
Yeah, absolutely. So when the penny dropped about the temperature, we then redid the dating trial on the same samples, and this time we carried out the experiment at 11 degrees C, which was the mean lifetime temperature of the material, and they all came out spot on.
What was it that you were dating at that point?
Oh, well, we had a range, a wide range of materials of different known ages, precisely known ages from the Museum of London. They were our collaborators on this. So we had pieces ranging from 2,000 years old to a week old, for example.
But they'd all been kept at 11 degrees C?
Well, not necessarily. Say the Roman brick, for example, that would have spent its life at 11 degrees C average temperature until it got put into the Museum of London, and then its mean temperature would have gone up. But over 2,000 years, because the t to the quarter law compresses the x-axis so much, even if something's been in a museum for a few decades, it's not going to really make any, well, it's not going to make any noticeable difference.
But how do you know the average temperature that an artefact has existed at? I mean, if it's really old, there probably have been blips, climate changes, all sorts of ups and downs of temperature over its lifetime. So how do you get to know exactly what temperature it was at? Well,
we arrived at 11 degrees C because that's the mean temperature in the southeast of England, where all these things came from. Yes, we've gone back 2,000 years so far. That's only because 2,000 years is the oldest sample that we've done. This is something we might have to take into consideration if we were looking at 16,000-year-old ceramics. I believe ceramic technology goes back 16,000 years. And then, yes, it might be an issue, but again, it's this compression of the x-axis, that if there's a little blip somewhere, you're not really going to see it.
Can you just explain what the t to the quarter law is?
Right, well, this compression is the t to the quarter function. The material will gain equal increments of mass in the time intervals 1, 16, 81, 256 minutes, years, decades, whatever units of time. So if you plot that on a graph, you go 1, 16, 81 is going to be out here somewhere, 256 is going to be the other side of the room somewhere. But if we take the fourth root of those numbers, we just get 1, 2, 3, 4 equally spaced. So the material will gain mass in equal increments of t to the quarter.
The method tells you how long ago the ceramic was fired, doesn't it? It doesn't necessarily tell you how old the ceramic is.
No. Generally, thermal events, historic thermal events such as bombs dropping or volcanic eruptions are well documented, so we are likely to know whether a piece of pottery has been exposed to a temperature higher than 500 degrees.
But this was a problem, wasn't it, when you were trying to get to grips with all this?
Yes, it was a major problem because we dated a medieval brick to be 66 years old. And, you know, these archaeologists keep incredibly meticulous records, and when Ian Betts at the Museum of London went back to his box of materials, he found that he'd made a little note, and the note said, surface vitrification of the brick indicates that it's been subjected to very high temperatures. And then we went back to where the brick had actually been found, and it had been found in Canterbury. It had 11,000 incendiaries dropped on it in the war. It had obviously, you know, heated it to high enough temperature to reset its internal clock.
So the method still worked?
Oh yeah, the method was spot on. It was us, yes. We also had the incident of a Roman brick dating to 8 months old. And that was a Roman brick that had been used in the first dating trial 8 months previously. So again, the method was right. It was actually spot on. It was 8 months since it had been reheated, yeah.
But you had refired it in that case?
Yes.
Yes.
You've just forgotten.
Now, what else might this method tell you? I mean, it must, for example, have implications for museums, the way that they store and display their ceramics.
Well, absolutely. I think just going back to this Roman tile here, you know, people have the perception that bricks, ceramics are just completely inert. Well, it's far from inert. At this minute, it's gobbling up water molecules and getting heavier and expanding. Because we're now in a room at 25 degrees C, we're not at 11 degrees C anymore. We've doubled its reaction rate. We've actually more than doubled its reaction rate. Now, they find when the archaeologists, when they excavate Neolithic pottery, for example, that it's turned to the consistency of cottage cheese. So that implies that a ceramic has a finite life. In other words, it will carry on expanding to the point at which the expansive strain can no longer be accommodated. It'll just disintegrate. So the hypothesis is that, well, the question is, how long, what's the lifetime of one of these things? How long have we got? Should we be storing things at low temperatures? Should we be creating a repository somewhere for our very, very valuable heritage ceramics to preserve them?
And this is one question, presumably, that you would really like to know the answer to. And to do this, you need more funding.
We do.
I know you are having funding difficulties.
Yes.
What are the sorts of questions you'd like to be able to answer with more funding?
Well, there are lots of questions. At random, in no particular order, how far back can we go? We've looked at materials that are 2,000 years old. We'd like to look at things older. The perception is that the technique is only good for 2,000 years. In fact, we've only gone back as far as 2,000 years. So how far back can we go? We've got to really undertake a systematic cross-validation exercise to, you know, produce confidence in the new technique. We've got to produce a standardised methodology so that we can take it out of our lab and take it from being a very challenging experimental exercise to the point where anybody could use it. On the more fundamental side, we really need to understand the underlying chemistry, you know, what's going on here. We just don't know. We also don't know what gives rise to this remarkable T to the quarter law. You know, we just don't know. And the other thing that is really vital in terms of archaeology is the precision of the method. You know, we really need to get a quantitative estimate of the precision of the method.
Thank you, Moira, very much indeed. And thank you for watching. That's all from this Royal Society videocast. We hope you'll join us again.